Okay. What is shown on the postal stamps? What do you typically see on postal stamps?
The American flag.
What else?
It's
Eisenberg.
I have stamps with little monsters.
I have stamps with the Rocky Mountains.
Okay, so here are the. I never saw the stamp. I found it on Wikipedia, but and you need to teach me either English or colloquial language once again. So, what's the name for this procedure when there is a potential couple and he or she, like, he's looking whether she will be favorable or not favorable to him, and makes a guess based on the
The like number of
Oh, the
petals.
flower
Yes.
petal thing? I don't actually know what it's called.
how single word.
Oh, God, it's the,
Word?
she loves me not.
Yeah.
I don't know what the word is.
Okay, so
There it is.
I'm the only one.
Yeah, I don't know the word for it.
No, I don't know the word. I don't think I've.
I'll just look at it real quick.
Okay,
There's like a name
He
for
loves
it?
me. He loves me not.
Yeah,
I don't
and then
know.
whatever you land on is like the truth of the universe.
Yeah,
Fortune telling.
Yeah.
person.
Predicting the future.
Okay,
yeah.
Okay. Predicting the future, and this attempt to make a humoristic post stamp in Germany, they put Heisenberg, who was answering the principle, and if you see a little subscript here, he is tearing off petals and was position, momentum, position, momentum.
There, it's it's a French origin, and it's literally called he loves me not, or, and I'm probably going to completely butcher this,
French word.
but if you're la Marguerite.
The last word is probably just the name of the flower. And before?
If you year,
Word, yes.
What?
uh,
What lecture are we on? 13? 14?
He sent it today. He like just.
Where? That is this.
no, sir.
I should.
I got it.
I learned something. Thank you.
We
Uh,
baguette.
So, what should I say to myself?
You can do it.
Back to the subject.
Oh, yeah. Lecture 15.
So, the goal, at the end of the meeting, we should arrive to this slide. What is the meaning of this slide, and how do we, why do we enjoy it? What does it mean? What does it stand for? I just feel myself a little too relaxed. Maybe you guys may start just telling me what is better.
Fred doesn't expect that I will approach you. So how do you interpret what do you see?
Well, up here, I see we have a Hamiltonian operator, and it looks like a version of the time-dependent Schrodinger's equation on the right side, but I could be wrong.
But,
It
okay.
just
Sure.
up top, it looks kind of similar.
Okay, there is a similarity with Schrodinger equation. It originates from it, but would you like to criticize Fred and say why it is not Schrodinger equation? Like Schrodinger equation deals with what is independent, what is unknown in Schrodinger equation, what we are looking to find. Schrodinger equation is an equation for. You know.
I feel like I don't.
You do.
Yes.
Energy is good, but what else? An abstract concept that
Position.
No, but you're closer. So predicting the future in terms of what? I think you.
Predicting like the future of like a location, of like the location of something that moves along like a wave.
Probability, location.
Closer probability.
I was gonna say, it's like predicting the probability of where something will be in the future.
Given the past.
You all are correct. I'm looking for a keyword, a word that is composed of two words.
I'm independent.
Right now, our goal is to criticize Fred.
Frank, that looks weird.
So he told that the red block on the top looks very much like time-dependent Schrodinger equation. And he's correct, but not 100%. So what is missing? Schrodinger equation, like there we want to find the unknown function is angular brackets of A. And in Schrodinger equation, unknown. You all were close. Okay, but maybe you try once again.
Is it potential energy?
No,
Kinetic.
no. That's I don't know how to push the thinking in the right direction. Okay, what do we I do not want to other side of the page.
Get around, kids.
Yeah.
It's really hard, yeah.
What do you remember in the middle of the night?
Right.
Plane wave is a particular case of what? What are units of plane wave? What is it like? No. How does it relate to probability? How does it, well, philosophically, you all are correct, but there is a name for a concept that we always solve for. Like, which weird symbols do you remember from this class?
Sign.
What is psi?
Size. What is?
Psi squared will be probability, and psi itself is.
Position.
I haven't heard. What is psi?
All right, let's.
Oh yes. Correct. So, wave function. So Schrodinger equation is an equation for wave function, right? And when someone Fred tells that upper block looks like Schrodinger equation, yes and no. There is no wave function. There is no psi symbol, right? Okay. I'm happy. We are moving maybe a little slower, but in the right direction. I was reading the word wave function in your eyes, but I didn't hear it. You know, like in cartoons about Disney movies with this stuff, and when he sees possible profit, there are dollar signs in the eyes. So I want you guys to have a size signs in your eyes.
Okay. I'll work on it.
Okay, so last time we derived, and this is not. I would say Heisenberg. And it is for A. So what is A? Oh, yes, correct. An operator can corresponding to the observable that we want to measure and predict.
Yes.
Right? And what angular brackets stand for?
Angle brackets. The vector? No.
Two brackets. Angular brackets. They're different from rectangular and they're different from round.
It's a vector.
If there is a one angular from one side, and then yes, then it is a vector. When it is angular from both sides. Now I will interview you guys, and then minutes later, Fred will give correct answer from the. Okay.
Is it like an orthogonal vector
Well,
or two orthogonal vectors? I guess?
if you would psi to the left, psi to the right, put them together, it will be their overlap. But if you overlap,
Yeah.
convolution, dot product.
Is it like a function of vectors?
Let me bring something up, and you will, I hope you will feel more comfortable, and I just need to be sober and do not forget my own question. So if, no, it is not what I wanted to do. So if you do have a row vector multiplied by column vector, row by column will be a number, right? Dot product. Now, if you do have row by matrix by a column, what are we going to get?
Like an equation, right?
Well, we all know how to multiply matrix by vector.
Oh. Expanding on that.
It's about this.
Oh.
It's pretty.
You know all the answers.
It's top left, top
R-
second, top right, third, row. Okay, I will be honest, I don't row by column.
Yeah, row by column. So let's apply, huh?
Another number?
Yes, it is a number. So we can put this in brackets. Matrix by vector will be a vector, and then row by column will be a number, right?
Yeah.
Now, if you replace this one, this one, this one, this one, this one, this way. So can you say anything how to treat this? What's a name for this construction? And whoever was presenting postulate number 4 was delivering this equation to us.
Well, like the, see, that's what, I was trying to look at my presentation. Things like that, and average.
Average is good. So that
In value.
yes, that is correct. So yes, so tell
I remember that it's expectation value.
but who needs expectation value?
I don't know.
Yeah,
Like what's it used for?
exactly. Like, is it a designed tool to torture young students?
Yes.
No. Like to give hard assignments, give poor grades.
Angular brackets mean that it's just like a number after you've like performed the operator on a certain function. And you use that to like, I don't know, get some value of momentum, probably.
Okay, very close. I'm happy to hear what Fred told. So right now we are general and abstract. So we do not say what A is. But if we can plug in anything that one needs to predict an outcome of an experiment, right? So observable is an abstract concept, and under observable one can put like NMR signal, UVV signal, maybe even energy of activation for reaction. And now we deal with a little simpler things like position and momentum, but because they're simple, later on one will escalate to more complicated observables. Make sense? Okay, so let me answer myself. To which question? Oh, who needs expectation value?
Yeah.
An experimentalist who wants to predict outcome of measurement before doing the measurement. So this equation is a bridge between abstract theory and practical experiment. So quantum theory itself deals only with operators and wave functions. And expectation values, it is something that one can measure in experiments. So if one wants to apply quantum theory to physical chemistry experiments, one needs to practice this equation. Okay. Now, if we believe the approach of Schrödinger, then our practical steps will be to, where it is? Yeah, here, to solve Schrödinger equation, five-way function, and then find this expectation value, which is good but long. It's like expensive. We need to dry our brain to make derivations which are longer. Heisenberg provided a shortcut. Now I'm just doing a recital of our Friday meeting because we need to warm up after the weekend. So the angular bracket A is a goal basically of the whole course. And instead of doing Schrödinger equation first and then this angular bracket protocol second, Heisenberg provided an equation that we together derived last time, which is in the top. So it predicts how the expectation value of an operator changes over time. And in order to do so, we need to make commutation. Remember Haha equation? You do? So H, comma, A in brackets means it is H. Click. So it means we have HA minus AH. And then right? Now, back to the point. From abstract to practical, we are dealing with still with electron in the free space, right? Electron in the free space means the Hamiltonian is equal to kinetic energy only, P squared over 2m, and potential is zero everywhere. Now, let's use this information about Hamiltonian and predict the results of observing average position, expectation value of position, and expectation value of momentum to predict future of our electron in the free space. Why are we doing it? When we started this chapter a long time ago, we agreed that we have two big scientific questions: how the center of the electron moves, and we guessed that it will move on a straight line. And second, how the shape of the distribution will change. And we already proved through our collective effort, both in class and in homework, that it will expand, right? So we did skip describing motion of the center on the language of wave function just because it is complicated. And here is a shortcut, although you may hate me and not believing me, but believe me, it is a shortcut. So we are focusing only on the position of electron, and we look how it changes over time. In order to do so, one needs to perform commutation between Hamiltonian operator and the operator of the variables that we are focusing on. Yes.
Equals.
What?
P squared over 2m is not supposed before. That's supposed to be.
It's letter H. Sorry for my calligraphy. I can surprise you more and more. Okay. And in order to see what is going on to be on the right side, we need to perform commutation. So basically, I think I'm wasting time, but in the regular lecture and in the rest of the, I need to prove like these steps. And then we will discover that the motion of the position depends on the expectation value of momentum. Therefore, we cannot do it on its own. So we will need to find equation of motion for expectation value of momentum. And then by plugging in the letter P, the operator P, into the red box, into Heisenberg equation of motion, we need to make commutation between Hamiltonian and momentum. We will find that it is zero, and we will find that momentum doesn't change over time. which agrees with our intuitive expectation that electron will move on a straight line on its own. But we are going to derive it and prove it more rigorously. Okay. So basically, we are done now. You can take popcorn, dim the light, and fall asleep. Right? And I will either go through the slides or derive something on the board, but there will be nothing more than that. And at the end, if expectation value of P is 0, we plug it in here, we solve this first order differential equation, that it will be initial position, and then the average expectation value of momentum or mass escalating as t, right? So moving on a straight line. Moving on a straight line and expanding the width. Whew. Oh, okay. Before we go to this, I want to remind, I don't know whom, to you or to myself, that by now we do have 3 cornerstones, 3 methods that we have accomplished in this class. What you see on the board is in some sense a table filled not with numbers but with equations. So our cornerstones are evolution operator, Schrödinger equation, and Heisenberg equation of motion. The first 2, the evolution operator and Schrödinger equation, serve our goal of on the way of connecting to experiment by predicting the wave function. So evolution operator predicts future based on the past just by evolution operator. Schrödinger equation instructs us to find eigenvalues, find expansion coefficients corresponding to initial condition, and then find wave function as this series, right? But both first cornerstone and second cornerstone instruct us to plug in this wave function into protocol to find expectation value, and then report it to experimental collaborator and include into co-authors, send paper, accumulate grant money or whatever, hire more students, and repeat the cycle. Yes. Oh, okay. The third one is a shortcut directly to expectation value of an observable, of an operator. So as soon as one knows the Hamiltonian, one can practice commutation between Hamiltonian and this operator, and there are rules of commutation. Your homework 3, problem 1 is one of the example. You will just enjoy doing it a little bit, but it's not so complicated. And then you plug in this result of this commutation into the equation of motion for the operator. And then by solving differential equation, one would find expectation value of operator A as function of time, same as in previous 2 approaches. Okay, so we are building like a pyramid of knowledge. Whew. The Schrödinger and Heisenberg approaches do have their strong and weak sides. So, and depending on which problem we will need to solve in the future, we will select either one of them. Although majority of people in the world select Schrödinger, it's not always the best choice. So number of degrees of freedom. Schrödinger equation in majority cases it's infinite number of degrees of freedom because a continuous function, wave function. Remember, Schrödinger equation is for wave function. It is something I was trying to pull from you this morning. A continuous function has many grid points to represent it. So basically infinite degrees of freedom. The Heisenberg equation of motion has only a couple of independent variables, the actual expectation value, like position expectation is an independent variable 1, and today we will see momentum is the second one. Sometimes it is like 3 or 4, but it's typically a very small number, treatable by standard methods of differential equations and solvable much more quicker and efficient. Mathematical challenges. One for Schrödinger, one needs to either diagonalize Hamiltonian or apply this huge evolution operator with matrix in the power of exponential, which is okay. For Heisenberg equation of motion, one just solves ordinary differential equations, which often is doable and can be done without computers. And in first two categories, Heisenberg wins, but in the last one, he is subject to lose. So in a very broad variety of problems, Schrödinger equation looks like a linear differential equation. Who takes or took linear differential equations? So what is a linear versus non-linear?
It's when the dependent variable, like when the derivative has a degree of more than 1, that's nonlinear, but if it's a degree of 1, then it is linear.
Okay, but even if it is second and third derivative, it's still linear. But on the left, like differential equation is a combination of derivatives of different order and independent function. And if independent function is appearing not in first power, but as a square or third,
That's still linear.
no,
No,
it's no.
if your independent is got a power of greater than 1.
No, it's
not.
the dependent one, because it's the one that we're taking, like the one that's like if y is dependent on x and the y derivative has like a second one.
No, if it's y, like if your function is like f of x, it's like y of x. You're like way to start y if it's to a power of amount.
Yeah.
But y would be independent. X.
No.
So y prime equals y is linear, y prime equals y squared is non-linear.
Yes,
Yes.
yes, that's what I'm saying.
Okay, and it is what I was saying. So we agree. We
Yes.
all agree. No conflict.
Yeah, you have dependent and independent.
I mean, you were describing.
And there are protocols to say how to solve with guarantee differential equation, linear differential equations with any level of complication, but for non-linear, there are no protocols. It is a matter of mathematical luck. You may or may not solve them. And the shortcoming of Heisenberg approach that sometimes it brings us to nonlinear differential equations, which sometimes have a divergent solutions when you slightly change your initial condition and you have qualitatively different types of solution. It's a big pain of a person who solves, but big fun to those who observe the solutions. Like change a little bit and then outcome dramatically differs. Okay, and we can represent our course as a walking, browsing in the abstract space of theories. Right? You don't like it? You hear it for the first time?
Yep.
So I didn't saw it. I'm not taking a credit, but I haven't seen it in the textbooks. It's probably just comes as an idea between people. So we do have a different level of complication of systems. Higher top will be real molecules and reactions. Right now we have just electron in a free space, and here x-axis will be different theories. So we have theory of evolution operator, theory of Schrödinger equation, theory of Heisenberg equation of motion, right? And z-axis will be external perturbation. When you do experiment, you want to do stimulus, response to a stimulus, like perturbed by light, by heating, by hammering, right? And if time allows, these perturbations will be at the very end of the course. But philosophically, the goal of the course is to populate the space. So have more methods and more systems where they are applied to. So right now we are on the beginning, we have one model and 3 methods, but we will have substantially more by the end of the course. So it gives you a little navigation of what we are doing. Okay. 12 minutes before the end, and we are starting the lecture. It was just a little introduction. So if our operator is x, Hamiltonian is the second derivative over x, and we do need to find commutation. Let me practice it, otherwise it will be boring. So I'll try to practice for a couple of minutes. If I fail, I'll come back to the slides. Video mute on. Okay. And is it okay if we all agreed with your
You can rush now.
I'm just looking so that I shouldn't go beyond the border. So Hamiltonian is p squared over 2m, which is minus h bar squared 2 masses second derivative dx squared. The operator a equals x, and then we need to practice the rectangular brackets, right? So in order to practice this, we need to, before we become big experts who know the answer with closed eyes, we need to assume that there is a little wave function here. At the end, we will remove it, but just to keep our mental sanity, we will assume that this is a combination of operators acting on some wave function. So before it was haha equation, now it's so minus h bar squared 2m d squared dx squared times x times phi. Now minus x times h minus times minus 1 h bar squared over 2m d 2 dx squared applied to phi. So
It's not right.
huh?
Wait, the sine minus.
So the Hamiltonian itself does have a minus, and definition of commutation has another minus.
Is that a negative one?
Yeah, negative one.
Multiplying minus signs? Or
I
is it
want.
subtraction?
Okay, let me do it this way.
It's a -1 times all that stuff. Yeah.
Better? Okay, so agree, no errors comparing to definition.
Yeah.
Okay, now we need to practice derivatives, and you all know how to do it. I'll try myself. If you would have more, if I would be speaking less, I would have a pleasure of inviting you to the whiteboard. So first term, dx product x times phi. Leaving first one outside, then product rule, right?
2d1 plus 1d2.
I will be trying to play very slow, or I'm really slow, times phi plus x times d phi dx. Errors? Yeah, or no errors?
No.
Errors, yeah, oh yeah, sure. Okay, and now doing the derivative once again. So applying to first, again, doing product rule, and then to the second. So d2 dx squared of x. By the way, this dx over x will be 1. This will be 0, right? Times phi
So it's 0,
plus
1.
x times d2 d phi dx squared. No?
No, that's right, I was wrong. So that's right.
Okay. And then the 2 more terms. No, I was wrong. I need to correct. I found no credits for you because I found my error myself.
Okay.
I need to learn how to
Plus
be.
one for me.
So, oh, thank you. So keeping dx over x intact and then d phi over dx here. So, okay,
Oh, yeah, I see
Right?
what you do.
you see?
No, exactly, yeah, I see what you do.
Okay, and now the next applying derivative to this term. So plus dx over dx times d phi over dx unchanged plus x d2 phi dx squared. So total 4 terms. Each application of the product rule doubles amount of terms. Yes?
I just want to press my back. I don't.
That's okay. That's okay. So this one will be 0.
Yeah, but there's an open one.
What else? Dx over x will be 1. Dx over x will be 1. Right?
Yes.
Yes. So you're so you do that, you get 2 get 1 plus 1 d2, which you come right then. If you do that again, you do 2. Oh, no, yep,
So
d1
2
plus 1 d2.
d phi dx plus
Plus
x d2 dx squared times phi. And now we need to put our function outside of brackets because we are going to drop it when we will be going further, right? So result of commutation is this thing. And
Okay, so I don't understand, why are there 4
I
terms?
don't understand where why do you have dx over dx? Like,
you don't
oh, that no mind. Okay. But
I would, it's my responsibility to explain if something is unclear at the step. What is unclear?
So I don't understand the
this makes sense.
fusion.
Okay.
And this makes sense,
Okay.
because if we do the partial derivative, 2 times the derivative of 1 plus 1 times the derivative of 2. So to
Wait,
me-
is it product rule?
Yes.
Oh, okay, I see now. I see now.
So 2 times the derivative of 1 plus 1 times the derivative of 2. Nope, that makes sense.
Okay, thank you. So everyone agrees on this. Okay, thank you. So I need to bring back the factors. I was skipping this minus. Just yeah, I was skipping this one, and I did only the, let's call it part A, right? Now I need to do part B. So another little derivation. Okay. So you see, it is doable, but a little like time consuming. So this was part A. Now we do part B. So x
Yeah.
d2 dx squared times phi. We do not have any ambiguity because the operator acts only on phi. The x is up front of it. Then we will need to subtract a minus b. You agree? So a includes first derivative and x times second derivative. B includes x times second derivative. If we subtract a minus b, then second derivative is gone. Yes? Okay. And now we do have only this part. So I'm going to pull it back. So minus h bar square over 2m times 2 d dx. And we can think of functions that we can remove anytime. Almost done. Well, not the whole thing that we need to do, but key part. Now, what is the definition of momentum operator? P equals plus or minus h bar d dx I and plus or minus? Minus, okay. You told it. If it is wrong, I'm not responsible. Now, let's compare what we have here and this definition. Can we see that there is a first derivative and here first derivative, and other factors can be played around, right, by multiplying and dividing. So can we, oh, 2 will cancel. We can consider it as h d dx, so it's still h squared, and now we need to multiply it by minus I divided by minus I and keep m, right? I didn't lie. And then this one can be treated as momentum operator, and this is just a factor. So it will be, if one can move I from numerator to denominator and change the sign, so I h bar p. Not we don't do expectation value, operator p. So by practicing commutation of Hamiltonian with position operator, we get momentum operator. You see? So they're conjugated to each other.
Doesn't it need to have an M on the bottom too?
It does. Melody plus melody plus 1. Well, maybe more will be more than 1 if I watch the lecture. I'm going to erase bottom and quickly complete the thing that we arrived to the logical conclusion. So now the Heisenberg equation of motion d dt over of x. So I over h bar, and then commutation hx, right? And now we replace this commutation by this thing. So I think I lost minus, so it will be, finding this minus will be my homework. But I times minus I will be 1. H bar here, H bar from there will cancel. And then we will have only P over 2, not 2, over M, which means change in time of the expectation value of position equals to velocity, expectation value of momentum, right? So I know that we all need to depart. I'll just quickly switch off, start our screen, share. So here is the derivation. So we perform this commutation, find the terms cancel, right? And then we arrive to and identify the momentum operator, bless you. And then we see that change in time of the bless you, of the x equals to expectation value of p. And then if we can integrate it and find that it will propagate on a straight line. There is a same thing for momentum, but it is quite simple. So let's finish meeting right now. Thank you for investing your time and your intellectual strengths. I know it is not easy. For me, it was the hardest subject at my time. So looking forward to see you and your homeworks in 2 days.